Welcome. How's it going today? Dr. Dan. Glad you're here. I've been seeing a lot of errors recently related to some two-dimensional geometry basics that I wanted to go over so hopefully you can make less errors in your work as you're working through whether your engineering program, geometry, whatever level of math you're working on. All right, so here we go. The first one to talk about are right triangles. We love right triangles, right? We love our friend SOHCAH and TOA, right? SOHCAHTOA. So sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, and TOA being the tangent is opposite over adjacent, right? So you all know those. The key terms in these, I think, are actually these two right here, this opposite and this adjacent. Let's talk a little more about that. All right, so what I'm seeing is students that are trying to break vectors into components, okay? So if this is a force component, and I give information that it is some angle here, theta from horizontal, I'm typically asking my students to say, hey, take this force, break it into an x component, a y component, right? X component we're going to say is horizontal, y component we're going to say there's vertical. Now, if I give it in this way, a lot of students, what they'll do is that they'll go ahead and say, all right, this x component, this one right down along here, this is going to be fx. And because they've done so many of these, what I call horizontal angles, right, they'll just, in their head, they'll say cosine is always x. And so they'll give that f cosine of theta. And that's right, completely and accurately right. The problem is if I give a system that looks like this, and instead of a horizontal angle, right, what if we're given here this vertical angle? Let's call this alpha, right? And so if you're stuck in your head that cosine is always x and sine is always y, it's not going to work on this one, right? And so, I don't know, call this p instead of f. And so now if we're looking at this x component right here, this p sub x, right, we're really looking at a right triangle that looks something like this, where cosine, as we saw up here, cosine is adjacent over hypotenuse, right? So the cosine term is actually going to be this piece right here. So this is going to be p sub y is equal to p cosine of, I leave myself enough room there, I'll squeeze in cosine of alpha. P sub x here is going to be p times sine of alpha, okay? So the big leap that I'd like folks to make is not think cosine x and sine y, but to think that adjacent, right, this is adjacent, coming back to our friend SOHCAHTOA, is going to be cosine, right? Adjacent is cosine, and then sine here is going to be opposite. Okay, and that will always put you on the correct track in sines and cosines. The other thing that's super critical on these, draw a triangle. Right? If you draw these triangles, your life is just so much easier to actually align, find those sines and cosines, instead of letting your mind kind of leap to conclusions, which may or may not be correct, right? So just give yourself a little drawing to get that accurate. The second thing that I'm seeing is students not being able to move angles around a system, okay? So let's say here that we have, there's a line, and there's a line. Right, and so I've drawn these two lines as being parallel. They're almost lines, they're not perfectly straight. Just want to talk through this a little bit, right? So if we know that this angle here, call this angle beta, then we can use a series of different rules, okay? Probably the one that people don't think of right off the top of their head, certainly the supplementary, complementary, students tend to have those down. But the one we have is a bisector of parallel lines, okay? And so these are the two parallel lines, this one and this one here. The bisector is this semi-vertical line right here. So what that tells us is that if we have a bisector of parallel lines, that this beta can be transferred up to this other angle right up here, right? And then the other piece, I think this is really obvious, is that these opposite angles here are also beta, right? And all of a sudden we have beta in 4 places versus only in 1 place. All right. I'm going to erase the board here for the last one, so I've got enough room. Thanks for sticking with me. All right, this last one here, we're going to take a look at finding the angle for 2 perpendicular lines, okay? And where this comes into play is, say we have a surface, okay? So here's my surface, And if I've told you that this surface happens to be, use blue here for this angle here, so if this angle happens to be phi from horizontal. Now, commonly, especially in statics and dynamics that I teach, we'll need to find basically an angle of a line perpendicular to this. Now, why is it perpendicular? It could be a normal force is perpendicular. It could be, we have a lot of terms in dynamics where we take a look at radiuses and velocities are always perpendicular for circular motion, just a lot of different applications. Okay, and so in this case, let's say we've got a force. So here is, say, some normal force perpendicular to that surface as we're drawing a free body diagram or something else. And let's assume we need to break this force into components, okay, into an x component, into a y component. And so again, we're assuming there with our axis system that we have a horizontal x axis system, a vertical y axis system like this, okay? Now, the number one tip I could give you on doing this is that I see so many of my students, if I give them a slanted line, they'll automatically draw it at 45 degrees. They think 45 degrees is just the perfect angled line. I'm here to make an argument that I actually draw 5 different kinds of angles, just kind of freehand. Horizontal, less than 45, at 45, steeper than 45, and vertical. Okay, if you can just discretize your lines into those 5 different types, you'll start to see these different angles a lot better than if you just pin everything at a 45. Okay, and watch how this works. So, I want to move this angle phi up into the space here for this normal force. Okay, now if you just simply take a look at this angle here versus this angle over here, because I drew this as less than 45, you should probably be able to see that this one and this one look like they're the same angle. And you're right. Let me prove that to you. Okay, and the way I'll prove it to you is I'm going to move this angle phi up here to that location right there. Now the reason I know that that's true is, again, I've got 2 parallel lines that are horizontal. I've got a bisector, so I can just move that angle up because those angles relate. The next thing I'm going to do, I'm talking about complementary angles. All right, so I switched a theta and a phi. I'll be honest with you, I often don't put thetas and phis in the same problem because with my students' handwriting, I can't tell the difference. So if this is angle phi, and we have a 90-degree angle right here, then we could say this other angle above it, let's just call it alpha. All right, so phi plus alpha, we could write this as an equation. Phi plus alpha equals 90 degrees. I'm going to call this phi 1, okay? Phi 1 plus alpha is equal to 90 degrees, or pi over 2 radians. All right, now if I'm looking for this angle over here, I can take a look at my system and say, you know what? By the way, it's also perpendicular from here to here, or over on this other side over here. So I could also then label, and you're going to see why here in a second, I'm going to call this phi sub 2, my second phi angle. And so down here I could write phi 2 plus alpha is equal to 90 degrees. So in order for both these equations to be true, to be valid, it turns out that these 2 phi angles must be exactly the same. Okay, and so I'm going to give these in words as opposed to a mathematical proof. What I'm going to say is that if you know an angle of a line from horizontal, any line perpendicular to this line is going to be the same angle phi from vertical. Right? I could really even erase these 1s and 2s because they're exactly the same line. I can even erase my alpha here just to make this really clear. But I'll say it again. If you have a line, some angle from horizontal, any line perpendicular to that line will be that same angle from vertical. Now, this also works, that flip of horizontal to vertical. Let's call this angle over here angle beta. And it turns out, I guess I could have also called it alpha here. Let's do that, right? It's actually the same as that angle alpha that I drew. So this is the same as angle alpha. Because I know it's angle alpha also because it's complementary to phi. So if I am identifying this line not with a horizontal angle phi, but a vertical angle alpha, then any line that is perpendicular to this one is going to be this same angle alpha from horizontal. right? So it's that horizontal vertical flip, that reference flip that we have for these two lines that are perpendicular in space. So one other tool I have to demonstrate this idea of perpendicular lines and the angles that reference them is if we think about this system here, and this gray part on top, this is going to be our surface and that perpendicular line to the surface, and the white on the bottom you can think of as our XY axis system. Okay, so I'm going to keep this horizontal and we keep this one vertical. And what we can see with these little yellow ties, right, is as we rotate a surface at some angle from horizontal, that here is this exact same angle from vertical. Right, and that's all we're really doing, right? Is we're keeping our axes stationary, and then we're rotating our object, and again sharing this angle, this one from horizontal, this one from vertical. Now, if I rotate this to this reference here, I can show that idea of, if our reference is from vertical, then our other surface is from horizontal. And so that could be shown maybe from here, right? So again, we're maintaining a vertical axis here. So this angle from vertical means that this perpendicular to it is the same angle from horizontal. I hope that helps. It's a common thing that, again, we use over and over and over. And some of these basic geometry, two-dimensional items are things that really can save my students a lot of errors and just do better things up front so they can get the right answers in the end. I appreciate your time today. Hope you're having a good one.